Yes, Bad Santa, it is the very last lecture of the term. Don't be sad. Okay, Sean, I won't be sad. This is officially my mind breaking, and this is Bad Santa. I just wanted to say that I've been really happy to have you guys around in this crazy time. So we're going to do one very, very last video lecture that'll give you a little bit of insight into something we're going to be doing a whole bunch of in second and third term, and that is answering synthesis type questions. One of the things that you'll notice about these more advanced looking synthesis problems is that there are several really important techniques to approaching them. So hopefully what I'll do during this presentation is I'll kind of model what we're going to be doing as we work through a synthesis problem. Another thing which I should mention is it depends very highly on your knowledge of note card reactions, which is one of the reasons that over the break I really highly recommend that you're making those cards if you haven't already and constantly looking at them so you're ready to go in second and third term. So the first thing that we're going to apply our kind of more advanced synthesis techniques towards is specifically alkyne type chemistry here. And one of the things that you'll notice is true of synthesis type questions, there's kind of like two different types, or at least the way that my crazy mind thinks about them. The very first one is what I call the friggin' dur, right? Where this is going to, these types of reactions, which you'll see some examples of, usually contain like a functional group that just kind of screams at you like, you should use this type of synthetic technique. The harder ones, the ones I'll kind of end this video with, are the ones where there's some sort of hidden type of sequence of steps. And those usually are something that you just need to get a bunch of practice with, have really good kind of sniffer looking for note card reactions and like really special functional groups that can only be gotten to by one particular way. So that's what the rest of this video is going to be about. For our first synthetic target, let's take a look at what I kind of consider a type 1 kind of synthesis problem. And so this is going to be our goal. And as I said, I'm going to try to model some of the steps that we're going to be using over the course of the next couple of terms. So the first thing is to keep in mind that I am going to probably not be thinking about this in a truly linear fashion where I think, okay, these are my starting materials, and this is the product that I'm going to end up with. What I'm going to end up doing is kind of working backwards in multiple different ways, and we saw that a little bit in the first synthesis lecture from last week. And I'm going to use these things called retrosynthetic arrows, which is just really a normal type of reaction arrow that's reversed in its direction, right? So these guys. And one of the techniques that really helps students to think about is that for everything that I suggest as a potential step, I always come up with two different ways that I could have seen the last step. So in other words, like I'm going to work backwards one way and then I'm going to work backwards another way. And what often happens is if you encourage yourself to do that, you'll start to see some connections that you won't otherwise see. So that's something that I'll probably kind of require of you when you do those first couple of synthesis sets next term, is that like I will force you to always kind of work backwards in two different ways, right? So diverge in the woods 2 times. So in other words, why I call this kind of a frigging dur type of reaction is if you can identify the alkyne functional group in a chapter that is called alkyne synthesis, it's pretty obvious where your equivalent of starting material is going to be. And so in this case, right, the fact that I see an alkyne, well, duh, I'm probably going to use some type of alkyne synthetic arrows. And really, the only reaction we know of at this point that ends up in a carbon-carbon bond are these types of the alkyne synthesis reactions that we've seen already. So it's a little bit simpler in this case. And so what I'm going to do is work backwards in 2 different ways and consider what the world might have looked like in order to get to this product. And then what we're going to do is we're going to just kind of analyze the system and kind of just talk about some like benefits or some kind of some different things that might make my synthesis a little bit more difficult. And in that hopefully will kind of allow us to guess which way I'd rather go in my synthesis. So here's what I've done is I've worked backwards using one of our acetylene synthesis type reactions, right? We know that if we have some sort of terminal alkyne, that H can get very easily ripped off by an appropriately strong base like sodium amide. And then we end up with the sticky N minus charge right there that attacks that carbon and kicks off that bromine. So as in any synthesis, right, it's all about just kind of throwing some things on a page, and then it's essentially a brainstorming session. And so I am going to just kind of leave that up for the time being. I'm going to work backwards yet another way, and then we're going to kind of compare the two to see any kind of benefits of one versus the other. So one advantage of a friggin' acetylene type synthesis is that if you can cut that bond and think about where that could have come from, we could just as easily do the other one. So let's do that, and I'll write down what this thing must have looked like beforehand. It looks very similar to the other one. Of course, we'd need some sort of strong base to deprotonate that end of the alkyne. And then I know from my note cards, or my those really important 3 synthetic note cards that we came up with previously, is that a ketone in the presence of this group, I get the attack of that sticky minus N there, and then ultimately I'd end up with this OH group on here. So now I've kind of satisfied that requirement, right? I've thought backwards at least 2 times. And so one thing that we should talk about is, how far backwards are we going to have to work, right? Well, it turns out that most synthetic questions, they'll actually give you some kind of bumpers on the sides, right? They'll say, you need to use the following starting materials to get to this particular product, right? Or sometimes it'll say, using only acetylene as your source of main chain carbons, you have to design a synthesis from there. Well, those are 2 very different questions, right? And so at least at the start here, I'll usually kind of indicate what you should start with, because what you can eventually, as we learn enough reactions, we can pretty much take any super complex product and work backwards until we're starting with like a 1 carbon containing thing, right? And so at this point, there'll be some reactions where you have to work all the way back to acetylene, other reactions where I'll say you can use this plus acetylene. And so let's just kind of pretend that this particular question allows us like one starting material of more than 2 carbons to kind of start with, plus acetylene, and how we might design this synthesis. So the first thing we have to do is anytime we come up with a couple of different ways to do things, we should really choose one, right? Maybe not be incredibly wedded to that particular one, but at least start to think about some advantages of either one. And honestly, at this point in your education, you may not know all of those considerations. And so I would never penalize you, and certainly in second term when we're just starting to learn this stuff, that you don't know particular types of chemistry that we haven't talked about yet, right? The important thing is just getting your mind thinking about it, and I can kind of fine tune it as long as you guys are putting the work in. So don't be concerned if this is something that's like super overwhelming to you right now. So let's say that I see a synthesis where I either have to do that as a last step or that as a last step. Well, I'll tell you what, I am 100% going to go with this one. And there's a couple of reasons that I say that. If you think about the type of reagent that you're using here, it's a really, really strong base, right? And so really strong bases are going to be on a lookout for any proton that they can rip off. Any acidic proton, in other words. And it turns out the protons here are not that acidic. There are some acidic protons here that we'll talk about. Turns out the most acidic proton in this process is actually that guy right there, right? And so we're actually going to use this set of reactions right here as opposed to using this. And the reason for that is this deprotonatable H right there. It turns out that the pKa of that particular functional group, being an alcohol, is much lower. In other words, a much better acid or a much more extractable proton than the H that's on our terminal acetylene here. And so what I'm going to do is I'm not going to erase it. I'm going to put just the kind of a dashed red X through it. And the reason that I'm not erasing it is that oftentimes this kind of idea may become important as we build some other part of our structure here. So that's one important thing, right? A bit important technique, work backwards at least 2 times. choose a path, but don't erase anything. So at this point, we have to work backwards, if possible, 2 different times. We'll see if that's possible here. This guy right here, actually this is the part that would be really difficult to make from acetylene. So we're gonna use this as kind of that magic reagent that I think I mentioned is, you know, more than 2 carbons. So this is the one thing that we're gonna use that's more than 2 carbons. So we're gonna put that out of our mind and we're just gonna concentrate on how I could have potentially formed something that looks like this. And if possible, we're gonna think in 2 different steps. Okay, so with my knowledge of note card reactions, what are a couple of different things that this thing could have started as? Well, we could, just kind of with analogy over here, is we could have imagined that bond, right, being formed directly from acetylene. And that's actually pretty pleasing to my eye, right? Because if you were to take this system and treat it with 1 equivalent, so that you'd only extract 1 proton, you could pretty easily react that with this other sticky end right here, this 2 carbon piece that, let's say, looked like this, right? And you can kind of notice that even though this looks very different than that, functionally, you're pretty much doing the same thing, right? And so that same starting material right there might have given me kind of an idea of what I had to use here. Okay, well, I think this looks pretty good, but just because Sean's a jerk, right, we have to think of another way that we could have gotten there. There aren't too many ways that we could have gotten to this point, but it's still worth writing down. There is one reaction we talked about that will produce a triple bond. It's a note card reaction, and so let's say that maybe I had this guy. Let's see, so just thinking about it, so there's my H, that's where I want my triple bond to occur, and there's my other 2 carbon piece, and I think, okay, well, I remember there was some way that I could get that to happen. Oh, that's right, that's that like crazy strong base, really hard reaction conditions, right, that we can actually get an alkyne to pop out of that thing. That, you know, that doesn't look as clean as this guy over here to me right now. So, you know, we'll keep that on the back burner. That might be a way that we can do something later. But for now, let's go with this right here. So we're gonna cross this out. Oh, and by the way, I put this starting material that originally went with this step right here, just up here, just to remind myself that I've already used that requirement for 1 material containing more than 2 carbons that I don't have to produce in the synthesis. The problem is that this guy right here, because of the fact that I need to go all the way to acetylene, now I've got a little bit of a problem, right? I have to figure out how the heck I could produce this. That's just acetylene, that's covered. So now I'm gonna kind of work backwards again, and maybe I'll work backwards up here. Right? How could I have formed this thing? Well, one way that I could have formed that is if I know my note card reactions. It's very easy to take some sort of double bonded material and introduce an HBr, right? This is just a normal hydrohalogenation or HBr addition to an alkene. Other ways that I could have done that, I guess that, I don't know, like there's a couple of reactions you don't know, but it turns out that this thing also could have been an alcohol. As I said, this is not a reaction that you guys know about just yet, but we will talk about. So there's another potential reaction. We haven't talked about that, so let's not use that one. Let's go here and say, okay, well, you know, there's my HBr. How did I make this? Again, a note card reaction. Well, I could have made that in 2 different ways. I could have started, in both cases, with an acetylene, and a reaction that takes a triple bond and turns into a double bond. We talked about 2 of them. One is going to give you H's on opposite sides of the double bond. One will put H's on H's on the opposite side of a double bond, and H is on the same side as a double bond. So in other words, I could use either dissolving metal reduction called the Birch reduction there. If you could read that, it's sodium and liquid ammonia. Here, of course, the stereochemistry of this doesn't really matter, right? Because it's just a plain old acetylene here. So I could have just as easily used H2 Lindlers. Right? It doesn't really matter. Oh, that one also, woo, it's getting crowded, is going to come from acetylene. So what you'll kind of notice if you look at this, right, it kind of looks like a mess. And honestly, like every single synthesis that we do, that's the goal, is to make it look like a mess so that I can see all of your thinking, right? And you'll notice that in each case, I worked backwards to 2, even when it was super awkward and didn't feel right. And that's going to be something that will really make you a lot better at synthesis. You just have to practice it, right? You have to force yourself to do this kind of thing. And I promise over time, it'll become a lot easier, especially as your knowledge of notecard reactions increases. So now let's come up with the full synthesis, right? And usually what you do is you take your kind of brainstorm session here. And at least for me, I like to just kind of like circle all the reactions that I like the most. Let's just say that I wanted to use this reaction. And let's see, cut out that reaction. And then this guy, except this guy is going to require that guy. We go and all the way to our product. And obviously that looks like a mess, right? And so what you're going to do is you're going to be really nice to Sean, and you're going to redraw that entire sequence of reactions from start to finish so that I can kind of see your final product. Okay, so here is that entire synthesis all written out nice and pretty. I always like to, just bring myself back to math class when like you get to the end of the proof and be like, whoa, I did it, right? So put a big old QED right there. So this thing kind of shows you all the steps. Make sure that I follow the rules. I only used one product that I didn't show produced from acetylene. I showed this guy, right, from here, right? And so that very first step kind of is going on here. That guy I then used in a second step. Really nicely summarized. So all of that put together, that's going to be the way that we answer some of what I call the more type 1 type questions. So let's take a look at a type 2, one where the functional group or the acetylene is a little bit hidden. So we've done now a type 1. Let me show you an example of a type 2 type of synthesis. And one of the things that you're going to notice about these is that even though they are more difficult, they're not necessarily longer syntheses, right? Usually I consider these I call them hidden for a reason, because when you look at something like this, right, we're looking for an alkyne and there is no alkyne there, right? And so what you have to really think about is how am I going to use that alkyne type chemistry and maybe a little bit of other chemistry that I have to produce something like this. And it turns out that usually these type 2 kind of problems, it really is kind of one step or sometimes 2 steps away from becoming a type 1, right? From you being able to recognize where the alkyne came from. So something like this, right? We don't necessarily have any reactions that produce a diol, right? This thing called the vicinal diol, directly from the alkyne. But one of the keys to kind of these hidden type problems is to have a really good knowledge of especially your alkene note cards and sometimes your alkyne note cards. That is there anything like one step away from this that gets me to an alkyne or something that I can work with, right? And so watch what I'm going to do here. So first thing I'm going to do is I'm going to try to work backwards and just think about anything that this could have been. Right? And we'll try to do 2 different steps here. And one of the things you'll notice is these type 2 problems, they're such specific last steps that usually if you try, you can't figure out any other way to do it than just one, right? And so here's a great example of something like that, right? The only real way that we know to form vicinal diols is through an alkene type reaction. So let's imagine that this thing is an alkene. Whatever alkene that you want to start with here. So that and a particular note card reaction is going to get us there pretty quickly. And actually, there's a couple of different note card reactions. So I guess really maybe that could be my second possibility, right? We'll work backwards to the same material, but we'll use a slightly different reaction. So again, knowledge of those note cards or having those note cards directly available to you are going to be pretty important. Turns out that this guy with osmium tetroxide, NMO, kind of a witch's brew type reaction that we've talked about in a previous video in a first step, and then sodium bisulfite. It turns out that if we take that subjected to these reaction conditions, we end up with a diol. Well, let's just do this reaction, which we haven't talked about yet. Turns out a really common synthetic sequence here. If you wanted to, let's say, end up with the other stereochemistry of the alcohols, which, by the way, we're not even going to talk about stereochemistry and synthesis just yet. A really common thing is to do metachloroperoxybenzoic acid, followed by a treatment with some sort of OH minus species. Turns out that that would actually end up giving me this. We, of course, we've talked about this reaction and the fact that it forms an epoxide, but we haven't talked about that one yet. So kind of leave that one off the wayside. Let's stick to this as kind of our step, our very last step. So now it's time to think about, well, I've got an alkene, right? Well, what are some different ways that I could get to an alkene? Well, there's a couple, many of whom, again, that you don't know, but the one that we have talked about is very specifically coming from an alkyne type of functionality that looks like this, right? And so what we really need to do is take something, and at least for this particular, this kind of synthetic intermediate here, we have to choose a very specific type, right? And so like, if I wanted to end up with this trans type double bond, we'd very specifically have to do that dissolving metal reduction. The thing is that technically here, that really doesn't matter, right? That since we're not talking about stereochemistry in this product, we don't really have to worry about the stereochemistry in that product. So that might make me think, oh, wait, there's a whole other type of pathway available to me here. So let's work backwards to, instead of this trans type product, let's imagine, well, this thing could have been a cis type product, right? In which case that this step could have been some sort of Lindlar's catalyst. Whoops, jeez. And of course, we would work backwards to the same exact alkyne. So all I'm trying to model here is kind of the way that you should approach these. At least the first, couple of weeks of doing these, you really have to have somebody that kind of guides you and gives you the feel for this thing. As your knowledge increases and as you guys work with more and more note card reactions, many, many, many more things will open up. But this is just kind of like, the way, again, that your syntheses should look. It's very rare that you can just look at something and go, oh, I know how to do that, right? It's usually going to take you kind of working backwards a couple of steps, working forwards from some starting materials. It turns out that this guy, right, once we've gotten to this point, it's pretty easy to work backwards because this is very similar to the last one. Right? It just turns out that what this thing would require is taking off each of these hydrogens in its succession and having them, let's say, attack some sort of chlorinated ethane type species. So, and of course, like in the last video, we talked about a really common synthetic technique for getting to yourself to some sort of chlorinated or halogenated material. Usually that means you've got some sort of alkyne that you've done some sort of reduction on that eventually, through a couple of steps here, we won't list them out again since they're really in the last video, of how to get to there. And then of course we would want to remind ourselves, let's just use sodium hydride, right? 2 equivalent sodium hydride there, plus 2 equivalents of that guy gets us to here, right? And so let's just kind of take a look at the way this whole entire thing looks. And again, I want to emphasize that type 2, like that's the part that really stresses students out, right? When they see some big, scary, crazy looking thing. Usually if you practice these techniques enough, eventually you kind of recognize like the hidden gems in there. Okay, so here's that beautiful picture. Just for some variety, I showed another way of writing Lindlar's catalyst there. I've got the HCl edition. I kind of wrote this out in a little bit more detail, that kind of like stepwise alkylation to form our terminal acetylide, or sorry, not terminal, internal acetylide. And then some reduction conditions to get to the alkene, and then our very final step. As I mentioned, right, usually that final step is the hardest one. I think we're going to stop here as opposed to building on this anymore. Probably when we start second term, we'll kind of see a few of these in the very first problem set. But until then, it's been a time.